Okay, so let me share my screen. So the first thing I want to go through is really quickly a direct server recorded video on the X site. I will probably upload it to YouTube and put a link, like just look at my YouTube channel essentially. Just if you go into like wherever it was you've been watching videos, it's sort of my like Alex Hoffman, then you can just look for my most recent video and I'll upload it there. I'm sure you all know how to use YouTube. Yeah, okay, I can try. I'm just pretty crap at Excite. It's very confusing. But I guess I've never really come across a university's hosting website that's good. They all seem to suck at this, even though they're full of computer scientists. Anyway, my first question that I'm going to is like, I'm going to do a couple of just sort of questions off the top of my head, and then we're actually going to work through cash questions from last year's exam and then the 2017 exam. So you can take inspiration from these heavily. But essentially, I want to firstly talk about, well, not talk about, but sort of use a question to describe. I need to do my touch screen. So is this working? Yes. So firstly, direct map cache is what we're looking at here. So to keep the course a bit quicker and shorter, I'm not going to ask you any questions about the other ones. Maybe just know that they exist, you know, and have a rough idea of them. If I say, quickly tell me the difference between direct map cache and fully associative cache, say fully associative cache doesn't use an index. It just maps it to any free cache line. That's all you really need to know about fully associative cache sort of thing. And then set cache, you can say it's a mix between fully associative cache and direct map cache. But we're mostly interested in direct map cache. Direct. Is my screen being shared, by the way? Because it's not highlighting green. My like text screen, is it being shared where I'm writing direct? Okay, great. So direct mapped cache. Now the address has the form of offset, index, and then the tag. So the offset, this is the one we use for looking inside memory block for our bytes that we want, the target byte. This is to find cache line. And this, I'll do an example now that will make this hopefully a bit clearer. And so this is the sort of like ID of block. And you'll see hopefully why I can use this large chunk of the remaining address as the identifier, even though, as you can imagine, more than one memory address in the system will share this portion of the address since it's at the higher end. So the question that I'm going to ask right now is, let's say I have, like for instance, so this is the question, I have a direct mapped cache that is of size, let's say like 8. And now I'm going to also say, in your exams, I will let you use a calculator. So I'm not sure where it stands. I'm going to have to message the admin and make sure that you're allowed to bring in a calculator. The calculations you'll need to do are super basic. You could take in like one of these ones that you give to children. But just to make your lives easier is essentially just doing a bit of divisions, because this is all the sort of maths that you're going to need for this. So if you're doing the exam in person at SIT, take a calculator with you. You will need one. Well, I mean, to be fair, these calculations can be done without a calculator. They're nothing. You should all be able to do these in your like head or on paper. But just to make it quicker, take a calculator. So let's say we have a cache of 8,192 bytes. And I'm going to ask you, or I'm going to say, in the case we have a direct cache of that size, and our cache line. So this is the memory block size, has a size of 64 bytes. Right? So now my question, so this is sort of like describing the system. Now, this will be like first question, how many cache lines are in my cache? Does anyone know the answer to this? Can anyone tell me? You just have to think about this. Six is sort of related to the to it, I guess. So if each cache line is 64 bytes, but my cache totals 8,192 bytes, how many cache lines do I have? Correct, exactly. So I'm just saying, like, number of cache lines is simply size of cache divided by line size. So we're dealing with 8192 divided by 164, and this gives us 128 lines. Now, let's go to the second question now, like the second part of the question, and I'm going to ask you these three things. Like, what are the sizes in bits of the index, sorry, the index, sorry, not the index, the offset. The offset, and you could think of this as, to make it, offset. This could also be sort of thought of as like the block offset. So inside of your memory block, this is like the offset of your byte, offset. The offset field, the index field, and the tag. And let's just say as well, assuming 32-bit system. So can anyone tell me how big our offset field would be? I think you've got it mixed around the wrong way. But you're sort of correct for some other stuff. The offset is the one on the very right-hand side that shows where your byte is within your memory block, within your line. So we think about memory address, like if we look here on the PLO I've written before, we're looking for this one here on the right, the offset. I think you had the answer is in what you've written, but you've just got to reformulate and rename the portions. I think you have it correct though. So what's the size of the offset? If we think we have 64 byte blocks or cache lines. So how many bits? I see how you've written it. I see what you've done. The offset is 6, index is 7, tag is 19. So tag is 19, yeah, and then offset. Well, let's go through it. So the offset, we have 64 byte blocks. So each address, so each byte has offset between 0, this is 0, and 63, right? So this can be shown in binary using how many bits? 64th bit is 0, 1, no, so 1, 2, 4, 8, 16, 32, 64, using 6 bits. So what did you have? Index 6. I think you just had it around the wrong way. So 6 bits to represent 0 to 32, right? Sorry, 0 to 64. 1, 2, 4, 8, 16, 32. Yeah. 6 bits. Exactly. So we have 6 bits to represent the offset, right? Because we have 64 bytes, so we can show this in 6 bits. So therefore, we have here 6 bits is the answer to the size of the offset. Now, the index, we know, for instance, we've calculated here that we have 128 lines. And so we do the exact same thing. Index. We have 128 lines. C question QA. Each line is therefore 0 and 127, meaning this, same as above, can be shown in binary using 7 bits. So we know that we have 6 bits here, 7 bits here. This is a 32-bit address. And so now hopefully all of you can see how big the tag has to be. It's literally just the remaining bits. Tag, it's the remaining bits, sorry. It's 32 minus index, so offset, we'll say offset. This is 6 minus index, 7, equals 19, right? So we have a tag of 19, which is exactly what Chan said. So well done. Now, so this will be like the first sort of question that I might ask you. So I think, is everyone good on this really quickly? Okay, so let's go a new page. Now, next sort of question I might ask you. Think of what I'm going to ask. So when we structure cache, cache is structured like this. Each cache line, so this would be, for instance, a cache line. We have more of them. This is the memory block. For instance, e.g., this is the 64 bytes. Now, when I was saying in direct map cache, when we want to look for a memory block, we go to the index, like we check the cache line, so we know which line it would be on. And then we compare the tag to see if it's the same memory block that we want. Meaning every cache line has to store the tag of the current block that's in there. So every cache line has this memory block, 64 bytes here, for instance, in our example, since I said we have a 64-byte cache line, but it also needs to store the tag of current block here. So my question would be to you, let's say, am I at C now? Yes, C. How much memory like this, what I'm saying is actual, I think double L, hardware, sorry, bytes, or on the silicon to create this cache. So can anyone ask me how, I was also going to ask me to sort of think, how would we calculate this? We know from even the questions, like the very beginning, the size of the cache. This means the storage capacity. Capacity, which is the sum of the cache line. But if I want to have, for instance, we've figured out we have 128 lines. What extra memory, like what other size do we need to store? Like actually on the silicon that makes up our cache. So if this is our entire cache here, and this is 128 lines, this size of all of this is 8,192 bytes. And each block needs the tag stored. And this we figured out was 19 bytes. Sorry, bits. This question is just from the top of my head. But I will upload this. And then after this question, we'll go through ones from actual exams. But I'll just write it down on the PDF because I'm not going to send you the old exams. Sorry. So how big would we, like what storage, what actual silicon, like bytes on the silicon do we need to create this cache? So the size of like the memory, actual size of cache, equals storage capacity plus metadata, and this is storing the tag, let's say current tag, come on, the current tag for each line, cache line. Let me save this quickly. So we know storage capacity was given in the question. 8,000 192 bytes. We know we know the tag is 19 bytes, 19 bits, sorry. Therefore, we need, and we have 128 cache lines. So we need 19 bits times 128 cache lines of metadata. So let me get my calculator, which I think is in the lounge room. 1 second. So we need 19 times 128. So we need 2,432 bits. So if we divide this by 8, we get 304 bytes of metadata. So our total cache size, so the total, or the actual, let's say that's probably better, actual cache size equals 8,192 plus 304 bytes. Does this make sense to everyone? Why this is the actual size of the cache? Meaning the size on the silicon, not the size like its storage capacity. When we talk about, oh, I have a 4 megabyte cache, a 4 megabyte cache is going to be actually need more storage space on the silicon because it obviously has to have stored the tag, meaning the metadata of each memory block for each cache line that is currently stored in the cache. Okay. Okay, so now we know in direct map cache, we have this, let's just do it. So we have the address like this. And let's do a super simple example. I'll take like an 8-bit system. So example, yeah, I'm on an 8-bit microcontroller. So memory addresses between 0 and 2 to the 8 minus 1. So, right, whatever that is. 2 to the power of 8. $256. 255, right. I didn't need to calculate for that. I'm a complete idiot. So this means that we have 255, like a length of 255 address. Now, let me like, we'll just, like the specification of the system is going to be like, I have a cache line of this size. I'm not going to ask you to like, I mean, I could be like, oh, I have a cache with this many lines. How big is each line? Or I'm going to tell you how big the lines are and tell you to tell me how many lines there are, right? So I can't just tell you to create the number of lines and how big the lines are. So one of them will be given to you, but we'll say, okay, I have a cache line of, let's say, what's 4 bytes, 4 bits. So 1, 2, 4, 8. So I have cache lines, sorry, I have 16 cache lines. Where's my eraser? Cache line, sorry, cache line of 16 bytes, right? And so this is just my system specification. And now every memory address on this machine maps into one cache line. So I know if I can do the math now, and let's say my cache is like, how big would my cache be? Let me find out an example of the sort of value that's sort of, yeah, okay, that's a good one. So let's just say cache line of 16 bytes, and my cache is 128 bytes. Oops. Actually, let's make it even smaller because I can fit it on the page. Let's just say is 64 bytes in size. So this means that on my system, my cache, if we look at my cache, if we do a calculation from the last question, we can calculate how many lines I have. If I have 64 bytes of cache memory and each line is 16 bytes, that means I just divide the size by the amount of bytes. This gives me, therefore, I have 4 cache lines. So if we think about how my cache looks like on silicon, I'm literally just have a block of memory. This is my cache. Divided into 4 chunks. And these are each 16 bytes. Totaling 64 bytes. Now, given some memory address, I'm just going to take some random 8-bit memory address. So like, let's say 0, it's a binary address. So we'll just get 1, 0, 1, 0, 1, 0, 1, 0. Now let's divide this up. From the last question, we can figure out how big our offset needs to be. Each block here is 16 bytes. So our memory address will either be between 0, 1, blah, 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 15. So we need to represent this with 1, 2, 4, 8, with 4 bits. So the offset is 4 bits. Now, this is my example instruction address. My program wants to run this instruction at this address in my main memory. When I compiled my program, the next instruction for my program is currently at this address in main memory. So we know I have 4 bits for the offset. So this is the offset. I know I have 4 cache lines, meaning I need 2 bits to decide which one of that is, because this is going to be the 0. This here is the 0, 0 cache line. This is the 0, 1 cache line. This is the 1, 0 cache line. This is the 1, 1 cache line. And this number is just here. So what it's saying is that for this address, I have the index equals 1, 0. Therefore, this one would land here. If this address gets into cache, it will always be in the 1, 0 cache line because the index in its address says 1, 0 in the index. It's literally just like, it's so easy. You just like, which index will this be in? You just read the value and you say that cache line. Super simple. Now this byte, if we think about the actual, so if we take this guy here and we'll make him bigger. So this is my cache line 1, 0. Now in here are lots of bytes. There's 16 bytes. 16 bytes. Starting from the memory, and we need 4 bits to represent 16 values. So here we have 0, 0, 0, oops, shit. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. And here, from our example, we have 1, 0, 1, 0 in the offset. So we know that somewhere in here is going to be the, like if we do ... there'll be the 1010 byte. So this is the whatever, what's 10? This is 0, 2, this is the 10th, like this is the 10. So this will actually be the 11th byte in this block. So we know that this memory address is would be in the 10 index cache line, and it would be in the 1010 byte of the cache line. Now, if we think about how can we tell if the byte that's currently, if this one in here is the right one, and this is when we use the tag. So I'll take another color. This is the green one. So this is the tag. And this is used for finding, is this block the one I'm looking for? Because you can imagine, if we look at all the memory addresses from 0 down to 255 in binary, there'll be the addresses like 1000, with this being the index, then there'll be like 1001 with this being the index, but they'll all land in different indexes, meaning different cache lines. So per cache line, there's only ever going to be one memory address that has this one tag. So we can use this tag to see, is the block in here currently the one I want? So we'd say, okay, we have this like metadata here, metadata, and this stores tag of current block. So maybe this block is already in memory. And so this metadata, in this case, we would have 2 bits of metadata for each cache line, might have 10 in it, meaning that this memory address has already been used and is currently in cache on this cache line. Therefore, the cache, like the lookup, just goes, okay, it takes this address, right? The one we have here, it takes this address. The first step is to look at the index. It'll then go, okay, we have this one here. This is the right, the cache line that we want. Then the second step is to look at the tag. And it will look here and say, great, they match. This is the correct block of memory in this cache line. Then it will just take the index and it will just go down that many spots till it gets to here. And it will access the byte in memory. And that's how the byte is accessed. And that's how direct map cache gets accessed. So hopefully this is clear.
That's a question.
Mm-hmm.
So for this case, right? The first thing that we do, we look at the index, which is 10, and we go to the third line in the cache, right? The third cache line. Then after going into it, because it's 16 bytes long, so we need to know which line we actually look, or which specific probably I don't know, address we're looking at. So we use the offset.
Yep, exactly.
10,
exactly.
10, right?
It's the index within the cache line.
Okay. And the reason why we have to use 4 bits is because this thing is 16 bytes long, right? So we need 4 bits.
So we're going to have
then
exactly, because it's 16 bytes, you'll have indexes between 0 and 15, which you can show with 4 bits.
Right. Okay. So so this is actually just an offset, which will tell you the kind of like the address, but after which
within the block.
Yeah, within the block, and then after that you go to that certain address, right? Then the actual value is not actually 1010, but the actual value could be something else.
It's whatever is in that address. Like correct, this here is just a byte. So this is our target data.
Okay.
In the whatever's stored in that cache line, like who knows what it is. This is the address. So this is the address here, and then this is accessing this data.
Right. And that data.
So this will actually be, in this case, this will be the instruction, because this is, for instance, this is an instruction address. Like if we were executing a program, the instruction would be stored in that line.
Okay.
Which is like what we talked about yesterday with Daniel, how you have like the op code and then like this machine code of the assembly.
Okay. So after we go to that area, then we check whether it is the actual byte that we're looking for with the tag. So we compare it with the tag, correct?
But you do the tag comparison before you use the offset. So firstly, you get the index and you go to the cache line, like here on the right, and there'll be the metadata of the current, like the block that's currently in the cache line will be saved up here. Like we have these 2 extra bits of the cache line that saves like, okay, I have this block. We'll compare them. So if this metadata is the same as the tag on our address, then we've got a hit. We know that the cache data is what we want. If it's a miss, like I was talking about in the lectures, we have to then go and load. We'll have to go to memory and get whatever's at this address and put it into that cache line.
Okay, so the metadata stores data of the current tag, right?
Yes, it just stores the current tag. And that's why I asked, for instance, in this second last question, we have a cache of 8,192 bytes. And we know we calculated that the tag is 19 bits long, meaning that every cache line has an extra 19 bits that aren't used for storage, but they actually just keep the tag of the current block in that line that we use for this comparison. And so that's why the actual cache implementation takes a little bit extra memory. We need this extra 304 bytes because we need to store, for each cache line, we have 128 of them, we need to store 19 bits. So we need to store 128 of these 19-bit tags as metadata to use for this comparison.
Okay, so actually then isn't this a redundancy? Because we can already address, or rather we can already go to the cache line using the index, but then we can also go to the cache line using the tag, correct? Because the tag is unique to each cache line.
It's unique to one memory block per cache line, right? Because if you imagine, let's just take this this memory address that we have here. So we have, if we list out all of the memory addresses that we can get in an 8-bit system, like 101010, the next one, like we'll have all of the 16 permutations of this, but then we would eventually get to 0B10111010, like whatever, like this doesn't matter. And then we'll keep going, and then there'll be a 0B101. Well, this will go back to 0. Sorry, this would actually end up being like 1, but up here somewhere, we would have 0B1001, whatever. And if we look at all of the possible tags that we can get, you'll only get this 10 tag once for each unique index. Meaning in that cache line, we'll only ever be able to get one memory block that actually has this tag or this tag, because this memory location would always end in the 10 cache line. This one would always end up in the 11 cache line. This one would always end up in the 01 cache line. And so these, like we'd have to make this complete, we can say we would also have the 0B1000 address. So this one would end up in the first cache line. And so these are the 4 addresses, or like we'd have all of the permutations of this crap, but essentially we have these sort of sets of addresses, and there's only going to be one unique set for this memory block in this cache line. And so we can use the tag to compare, is this the correct block?
Oh, okay. So the tag is for that specific cache block.
Yes.
So we have different, like L1 cache, L2 cache, L3 cache. So this tag tells us which block.
It's not the level, but like if we expand this even further, look at these addresses here. We have 0B. We're interested in the addresses that have the 10 tag. So we're looking at, let's just delete all of this to make it really clean. So we want 01, what was it, 01 tag? Yeah, no, 10 tag. 10 tags. Now we know that our cache lines are 16 bytes. So we're going to get there's the addresses of 1000, and then this will be 0 to 15 here. Like there's a set. So this is going to be a set of 16 addresses but this is just one memory block. Because this whole memory, this address references a memory block that would completely fill cache, like this line, right? But we're only interested in memory blocks. We'd have the 0B1001, sorry, 01, and then also this would have the 0 to 15 because this is the size of the block. We'd also have the memory address. Oh, here we're missing 10, and then this would be, come on. 0 to 15. And finally, so if we look at our cache lines here, this one goes to cache line 0, 0, 0, goes to 0, 1, goes to 1, 0, and this one goes to 1, 1, right?
Yep.
See this, how they all end up on different cache lines? Here, well, what do we do the offset in? We did the offset in red. This is essentially just the offsets of each byte in the cache line. But now, if we look at the tags here, they're all the same, but you'll only ever find one memory block with this tag per cache line. So for example, cache line 0, 0 will only ever have one block with tag 10, i.e. address 0B1000 and then the 0 to 15 bytes at the end. See this? So we can say that the tag is unique. There's only one memory block that will ever have the 10 tag for a certain cache line, and therefore we can use it to compare, is this the current memory block in my cache line? So then we know, okay, yes it is, I can use it, or no it's not, I need to read it from memory and put it into the cache line because I've had a hit or a miss.
Okay, so that means that block, what does block mean? Block means your memory, is it?
This memory size. So what I'm saying here is that the question that I sort of said, we have a cache line of 16 bytes. So each cache line is, like we've written here, is 16 bytes long. This is 16 bytes. And so this memory block is 16 bytes. And this is why as well I have this sort of squiggly, because there's going to be 16 addresses in this block. And so this actual address references a block because at the end we have all of these 16 different combinations to reference all of these 16 bytes that are in my block. So I hope I got to keep moving because otherwise we're going to run out of time. So the difference, I can wonder if I can copy this over. Or the only difference then, if we look quickly at fully associative cache, the thing is we don't have an index. So you can imagine the same thing. Let's say we have same cache example, which means 16 bytes, lines, 4 lines, all right? 4 lines, like up above here. Same example. But what happens in this memory is that we'll have our memory blocks, right, with some tag and some offset. And this is like all our memory addresses. Mem. whatever, all the way down. And these can all just get mapped into cache. So into our 4 lines, these are our cache lines. They can just go completely random. Like this one can come down here, and then this one goes up here. And then if we had like another one, this could go up here. And so this would store like the tag. For instance, if we had like tag here, say we have like the tag here, and this tag would get stored in the metadata, right? In this like little metadata thing here. And so we also get, for instance, here, like in green. So we'd have the metadata storing the tag. And so it's just completely random. It looks for an empty location in cache that's not occupied, and it fills it. And if it is full, it just gets rid of something, maybe just randomly, and fills it. And so you can imagine searching for cache or searching for your entry now is very simple. The tag is much longer because it also contains the index. Like it's, so you have much longer tags, but you just step through, like searching means you just step through cache, and compare tags. So it takes a lot longer to search because you're just literally stepping all the way through cache and comparing your tags. And then set associative is sort of a mix between the two, in that like you have a small index that tells you like a region of cache lines that you could be in. And then within that region of cache lines, it's random allocation. But I won't go through that. I think you can rewatch the lecture because we've only got like another half hour. I want to get some more questions done. Okay, so now I'm going to look at a question. Which one was I wanted to do? This is an old exam question. Where's... So this would be, this is an old exam question, and we're going to work through it now. So let's have a look. We assume we have a direct map cache with cache lines of 64 bytes, a tag of 16 bits, and 32-bit addresses. How many 32-bit instructions can be stored in the cache? So we need to figure out the cache size, right? But we'll just sort of break this down. We know, let's draw out sort of our address. So our address looks like this. We have 32 bits. We have a line size of 64 bytes. So let's think about like this is the same as the last question. So this here, offset, needs to show 0 to 63. Therefore, it has to be 6 bits, right? 1, 2, 4, 8, 6 bits, exactly. how many 32 bits, Now we need to figure out a tag of 16 bits. So we have a tag here of 16 bits. And so how big is our index going to be? Index is therefore 32 minus 16 minus 6. So we have 10 bits. So it's 10 bits in size. So index equals 10 bits equals 2 to the 10 possibilities. And this equals, if we put it in my calculator, what's 2 to the 10? 1,024 cache lines. So we know we have 1,024 cache lines. Let me just see if I always get my chat. Yeah, very good, Chen. Now, the first question was, how many 32-bit instructions can we be stored in the cache? So we sort of just need to know how big is my cache, because if we have like this many bytes, we just divide it by 4, because 32 bits is 4 bytes. So for question A, we need to know cache size, because answer is cache size divided by 32 bits instructions. This is 4 bytes. So to get our cache size, it's pretty simple. We know how many lines we have, and we know how big each line is. So it's a simple multiplication. So cache size equals 1,024 lines times by 64, was it 64 bytes? 64 byte, yep, 64 byte cache line size. So this equals whatever this is, 65,536 bytes. Now, this is my total cache size. So 36, yes. And so this means we can store 65,536 divided by 4, 32-bit. So just to make it simple, this is 4 bytes instructions. We can store 16,000. We can store 16,384 instructions in our cache. Hooray. So hopefully that makes sense to everyone. Now, how many cache lines are there in total? So we've sort of already answered this in figuring out the first one. B, oops. What is the total amount of memory required for implementing such a cache? Not include counting the valid bit. So there is no valid bit in direct map cache, but anyway, their mistake. So let's go and figure out, this is the exact same as last time. So our tag, what is, how many bits? Tag is 16 bits. Therefore, we need 16 bits of metadata for each cache line. Therefore, total metadata equals 16 times by 1024 cache lines, right? 1024 cache lines. So we have like 16 or something, 16 times 10, 24, 16,384 bits. Now this is important. This is bits. So this equals, if we divide this by 8, 2,048 bytes of metadata. So therefore, total memory equals cache size, cache capacities, let's say, plus memory needed for metadata. So this equals how big was our cache? We figured this out at the beginning, or did we? Cache size, here we go. So this one goes down. And then this one is down here. So what was it? 65536. Oops. $67,584 bytes. Now, please, in your exam questions, write down for me when you give an answer if it's bits or if it's bytes, because sometimes it's quite important. So don't just write a number, but write down bits or write down bytes so that I know that you're not mixing them up. Because for instance, here, if you wrote 16,000 bytes, this is completely wrong. Okay, so that's the answer. That was that exam question answered. Now, I want to do one more exam question, which I think will actually get done, which is great, which is very similar to these. You'll sort of see like this sort of pattern of questions that we'll ask you. Let's see if there's anything else. Nope. Now, since we have 20 minutes left, I think we have enough time for you guys to sort of take lead on this question. Assuming a direct mapped cache instructions that tell us how big our system is. Well, let's have a look. If 10 bits are used for the index and the cache capacity is 16 kilobytes, how much additional memory is in the cache to store the tags? I think this must be a 32-bit system. Yeah. So this is a 32-bit system. I won't, Chan, like I can't penalize you. Like I won't be like, oh, you forgot, but I don't know. They're two completely different values. So you need to let me know, like, is it 16,000 bits or 16,000 bytes? Because 16,000 bytes is 8 times bigger than 16,000 bits. Do you know what I mean? So on this question, let's have a look. How would we go through this? An easy way to start is to draw a picture. Oops. Ten bits are used for the index. Oops. Tag, offset. We need to figure out how much memory we need to store. So 10 bits are used for index and the cache capacity is blah, blah, blah. So we need to figure out the size of the offset and the tag. And I think we have, or I mean, we're assuming we have everything we need, the information to figure this out. So how can we figure out how big our offset is? So let's think about the offset equals the size of cache divided by number of lines. So we need to get those two unknowns. How big is our size of cache? But more specifically, we just say this is 16 times 10, 24, right? Like here. And just a quick note to everyone. This is generally, little b is generally used to describe bits, and a big B is bytes. Just fun facts. So I could also say that this is, get rid of my European numbers. So there, now we know the size of our cache. So the number of lines, how do we figure out the number of lines? Yep, perfect. So we know we have 10 bits telling us our index. Therefore, oops, we have 2 to the 10 cache lines, which is 1,024 cache lines. Now we should be able to go out and figure out how big is our offset, right? Offset equals 16, yeah, could be. So offset, go down, equals 16,384 divided by 1024. Yeah, perfect. But this tells us how many offsets we have. Sorry, I should probably say this differently. This is not offset. This is block size. Right? Size of cache, number of lines. Or this is even better, it's block/line size, right? So this means our cache line is 16 bytes, meaning how big is our offset? Like how many bits is our offset? Yep, 4 bits. So we can put this in here, 4 bits. How much additional memory is required in the cache to store the tags, right? And so this here is saying how large is our metadata in bytes. That's essentially what the question is asking. It wants us to calculate, okay, we need to find out how big every tag is. And then we just say, okay, we need per cache line this many bits to store the tag. So we just find out how big the tag is and multiply the bit count of the tag times by the amount of cache lines that we have. So we know how many cache lines we have. We have 1024. Now we know we have a 32-bit tag, 32-bit address. So we'll say, go to black, 32-bit address. Therefore, tag bits equals 32. Oops. Come on. 32 minus, so this is 10 for the index, minus 4 for the offset. So we get, what's that, 14, 20, 18. 18 bits for the tag, right? That's my mouse. Okay, and so then we can say, we now know, therefore each cache line requires 18 bits of metadata. Therefore, the cache requires a total of 124, which is our cache lines, times by 18 bits. So we need 18,000, 432 bits. This equals 2,304 bytes. So the cache line you wrote on top left. That's the size of each cache line, and this is the number of cache lines. Yeah. So therefore, we have 2,304 bytes of metadata. So therefore, the answer is not asking for the total size of the cache. In this question, it's just asking for this. So the correct answer to this question would be this here. That's the answer. Now there's a second part to this question. Let me find it. Oh shit, did I close it? No, I didn't. So now consider a different cache that can store 65,536 bytes of user data and has an index size of 8 bits. How many cache lines are there? So let's draw a picture of our address. What have they given us? Has an index of 8 bits. 8 bits. Offset is unknown. Tag unknown. How many cache lines are there in total? So number of cache lines equals offset. Yeah, sorry, let's just say 2 to the number of cache lines equals offset. Wait, no. 2 to the offset, 2 to offset bits. There we go. So how can we go about figuring out how many cache lines there are in total? What can we figure out from this? What of these, we have 2 unknowns, number of cache lines and the offset bits. The offset bits is essentially what we're trying to figure out. How can we figure out the number of cache lines? Oh shit, no, this is completely wrong, sorry. 2 to the index bits. My bad. What you've, so Chan has just written, is it 65,536 divided by 2 to the power of 8? That would give you the size of each cache line. So that is the answer to B. But you've got half of the answer, like you have the correct answer in there, in that we just want, so the number of cache lines, so we'll just go, equals 2 to the, oh sorry, I just don't even need this, 2 to the 8, which equals, what, like 256 cache lines. Right? Yep. And so now for B, like as Chen said, how big is a cache line? So size of cache line is obviously just cache size divided by number of lines. Right? This is what Chan said, which is 65,536 divided by 256, which gives us whatever that is. $256. And this is bytes. Make sure we put down the B, the big B for the bytes. Okay, and so now we should be able to figure out C. So what's missing for us to figure out the tag? What don't we know? Well, we kind of do know it already. Exactly. We know the size of a cache line. So Chan, can you tell me how many bits is our offset field in our address? Yes. Like Elliot said, how many bits do we need to represent our offset? We know that we have 256 bytes per line, like you said. So therefore, the number of offset bits, let's just say it's K, comes from cache line size equals 2 to the K. So this is the amount of bits here, K. So we have 256 equals 2 to the K, therefore K is 8. Offset is 8 bits. So 8 bits here. So then how big is our tag? Yes, right? 8832, yep. Therefore, tag is 16 bits. And, oh yeah, that's the answer. So that's the end of that question. So if you've understood this, you should be able to answer the questions that I'll ask you in the exam. So now, has anyone got questions to what we just did? Okay. So if I take, for instance, like right up here, where I did this example, let me draw this example out a bit different again. So we'll sort of go through the whole process again. So we have 8-bit address, 8-bit address. What else do we have? Like a 16-byte, 16-byte cache line, 64-byte cache, i.e. 4 cache lines. So we have our cache here, and then like in memory, we'll have our actual, this is in like in RAM, we'll have our addresses going from 0x0000, so it's 8-bit. Oh wait, sorry, 8-bit is even smaller. So we'll have memory addresses going down to 0xFF from 0x01, right? And so our cache is going to look like this, in that you have 4 cache lines. So if we have, for instance, an address, example address, in binary would be like 101010. I'll actually make it something a bit different. So here we have 4 cache lines, and we can say that this is the cache line. All right, we know actually that we have, this represents 0 to 15, and this comes from the size of the cache line. This is just to reiterate this. We have 4 cache lines, or let's do this in a different color. 4 cache lines, therefore we have an index. This is the index. Meaning we'll have the cache lines 0, 0, 0, 1, 1, 0, 1, 1. So this is just sort of how it is. Like in each one of these is like this will be 16 bytes. Right? And this is sort of coming from this. This is coming from this again. And these guys will be 0, 1, 0, 0, 0, 0, 1. Actually, sorry, even. There'll be 0, 0, 0, 0, 0, 0, 0, 1, blah, 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 until we get down to 1, 1, 1, 1. So these are the offsets of each byte. So that's just how we sort of have our 16 offsets within each cache line, and we have 4 cache lines because we have this here, we have 2 bits representing our index. And how we would then go and search, like if we picked out here so what is actually this guy in binary is, in hex is 0x 1, 2, so 8, 10, so 8, 12, 14, what's that in hex? A, B, C, D, E, E, 1, 2, 6. So this is E6 in hex. So here we'd have 0x E6 somewhere, right? Here is here. And so if we want to see if this memory address is in cache, we'll pull out, we know that we want to load E6, which actually unpacks to look like this in binary. So the first step, so let's find E6. And this is this guy up here. So step 1, find cache line. This just means read it off. Read it out of address. Equals 1, 0. So we go to this cache line. Now we need to know if E6 was already loaded into cache, right? And so E6 has this sort of offset, but we just want to check is the right block in memory. So we need to know if the 1, 1 block, like a block with this here, is in memory. So the metadata is used in that each cache line stores a few extra bits that store the tag of the current block in it. So this could be, for instance, any number. Since we have 2 bits for the tag, this could be any number, metadata. And this could be 0, 0, 0, 1, 1, 0, or 1, 1, since we have 2 bits for the tag. So for instance, if we wanted to see if E6 was in the cache, we would have to just check this metadata and see if in the tag here, to compare tag, compare 0xE36 tag to metadata, to cache line metadata. If metadata equals 1, 1, so this is this guy here, then hit, we hit, else miss. So if we have here 1, 1 stored in that metadata, then we know we've hit, that the block we want from memory is already in cache. And so we can just access it and read it, and it's really quick. If it's not, so if, for instance, the last block to be loaded in was 1, 0, so like if last block, so actually I should write this maybe like over here, take a different color. If last block was for example, let's say 0B10101111, meaning that this also goes into the same cache line. Oh, sorry, that's the wrong way, that's the tag. Also goes into the same cache line, but you would end up with this guy going into the tag. And so when we were then to go to look for E6, we would be looking for this like 1-1 tag. And so we would compare it to the current metadata tag and see that it's a different tag. And so therefore it's not the same block. We currently have this 1010 block in memory. So then this is the second step. And then the third step is only for if hit, access byte given by offset. So in this example, we would just go down to, where's my mouse? We would go and look for 00110 and access it. Else load correct block into cache. And this would mean that we would go from memory and we would take him, oops, shit. We would take him, we would put him into the cache line, and then we would set the tag to be the correct one, which was 01. So meaning the next time we went around, if we wanted to access the same block twice in a row, now we'd have the correct tag in our metadata and we would get a hit. Not in the RAM, but in the cache. Cache has 4 lines and each one stores a block. RAM can have like any number of blocks, but each block will have exactly one cache line onto which it maps. So then are there any more questions? Hopefully this sort of explains it. I think if you watch this back, I'll upload this to YouTube now, so it should be up online in about an hour or so. You can watch this back a couple of times until you understand it. Okay guys, then I'm gonna end it here and I'll see you guys back tomorrow for the last hour of worst case execution time. And then I wanna sort of, if I have the time, start going through some of the exercises for worst case execution time. And the tutorial, maybe we'll have time to do some more programming. Maybe if you're very motivated, try and have a look at it yourself. Because we need to also do some more exercises, like written exercises tomorrow as sort of like examples of the exam questions. So I'll see you guys tomorrow. Let me say, stop recording this. Do you want to sort of, if yes, you receive it here.